So we're done with chapter 2. We're not going to worry about sections 2.8 and 2.9 because that will naturally come up later on in the book. Those particular concepts. But we need to talk about determinants. We need to talk about determinants. So I have an example here. Let me give you a moment to copy the example down. Okay. And Matthew, regarding the exam, so I'm thinking I'd like to have it, the next exam like this one. One thing I'll mention too, I know you're copying the example, but you know when you get a problem like you know, like let's say the exam you get a problem wrong, and then you try, you get a problem wrong, but then you can go and review the exam and see the answers, and then try to figure out what you did wrong. And then the first remediation, you go to the first remediation and try to redo a similar problem. And that's good. But of course, if you miss that same problem, again on the first remediation, then I expect you to go to the second remediation. And if you miss that problem on the second remediation, then I expect you to go to the third remediation to try to get the problem right. Okay, so you know, it's understandable. That's why those remediations are there. I can't really give credit if you miss a problem and then you just, you know, don't try to get it right on the remediations, right? That's the purpose of those remediations. So just keep that in mind. Many of you did the remediations fine, but I just want you to understand, you know, when you miss a problem, you're supposed to try to get it. You want to try to get it right on the remediations, right? Because that's how you're going to get credit, right? Okay, all right, good. So we want to do the determinant here. Compute the determinant using a cofactor expansion. Okay, and yeah, we did do determinants for 2x2 matrices. So like for instance, if you have like a matrix, well, let me just do a determinant here. So when we compute a determinant, the notation for determinant is absolute value signs. Okay, how many have seen the absolute value signs for a determinant? Okay, Matthew has. Solomon has. All right. And Christy has, and you're going to see why determinants are important. But anyway, what I have here is a 2x2 determinant. And the way you compute a 2x2 determinant is very simple. You take the product of diagonal entries, the first one being from left to right, 1 times 4. And then you subtract the product for the other diagonal entries. That being, maybe I'll put that in black. That being, in this case, 3 times 2. Trying to be neat with the mouse. Getting better at this mouse. Okay, so 2x2 determinant, that's how you compute a 2x2 determinant. But in linear algebra and other fields as well, you have determinants that of bigger square matrices. By the way, a matrix has to be a square matrix in order to compute its determinant. So when we have larger matrices, we use something called cofactor expansion. Now, I'll just mention this in passing. For a 3x3 determinant, there is a procedure. I don't know if you've seen it. If you took multivariable calculus, maybe your professor might have taught you this, where you can write down the first two columns and then like multiply the elements this way and then subtract multiplications going the other way. How many have seen that, maybe seen that kind of thing? Okay, Mikhail has, Divar has, and that's good for calculus 3. But the problem with this approach is that it's only good for 3x3 determinants. You can't use it for a 4x4 determinant or higher. That's right. And so you can't use that approach. That approach is not allowed in linear algebra, even though it's allowed maybe in calculus 3. In linear algebra, you're going to need to use cofactor expansion. Okay, absolutely. I find it kind of, you're going to like this way better. So what you do with cofactor expansion, it's an expansion. And the proof of it, they talk about how a little bit in the book regarding it, but you're just going to, for now, take it on faith. You're just going to take it on faith, what I'm showing you. So we're going to do an expansion. So what is this cofactor expansion? Well, to compute the determinant, okay, we can use cofactor expansion along any row or any column we wish. Okay, so let me give you a moment to copy this down. Okay, so what we're going to do is we're going to do a cofactor expansion along the first row. Okay, we're going to do to compute the determinant. So the actually doing this way works pretty nicely because I can use the mouse to show you a few things. All right, so what we're doing is we're going to use the first row. And let's take a look at the number 1 here. The number 1. Now, that is, in terms of notation, that is the entry A sub 1, 1, right? A sub 1, 1. Because that entry, that number 1, is in the first row and the first column. Okay. So in computing the determinant, okay, what we do is so here I'm doing the determinant of A, and incidentally I have DET space A, but I could just have easily had absolute value of A. It isn't the absolute value, it's just notation for the determinant of A. So I write down the entry 1, and I multiply that by -1 to the I plus j power. But because 1 is in the first row in the first column, the power is going to be 1 plus 1. Okay, that's going to be the power. Okay, and then what I do is I multiply that by the determinant of the submatrix that results. Notice this submatrix here. Maybe I'll put it in purple. This is a submatrix. It's a 2 by 2 matrix. Oh, how did I get that 2 by 2 matrix? Well, actually, it's the determinant of a 2 by 2. How did I get that? I crossed out the first column and the first row because the number 1 is it's the entry in the first column and the first row, and this is going to leave me with this submatrix for -1, 2, 0. Okay. The C11, which is defined as -1 to the 1 plus 1th power times the determinant of 4, -1, -2, 0, is a cofactor. It's a cofactor, and we're going to have 3 cofactors because we have three numbers, the 1, 5, and the 0. So the -1, just take it on faith that it belongs there. It's part of the formula, and that's why it's there. Good question. Good question. All right. Now what we have to do is we have to go to the 5. So let me just clear the writing there. Now, hold on here. Let me just let me circle the first row, 1, 5, 0, because I'm expanding along the first row. But now I'm going to focus on 5. 5 is the number in the matrix. It's the element that's in the first row and the second column. First row, second column. Okay, and so now what we do is we multiply 5 by -1 to the 1 plus 2 power. First row, second column, 1, 2. Okay. The respective coefficients for each term is phi. I'm not sure. Well, what we have to do now, this 5 5 is the second entry. No problem. And keep in mind that the 5 is located in the first row and the second column. So if we cross out the first row and the second column, we're left with 2, -1, 0, and 0. And that's the submatrix there. And we're going to compute the determinant of that. That's a 2 by 2. 2 by 2, right? So this is the second cofactor. Are there any questions so far? All right. Well, let's proceed on. We got one more. Now this is a 0, right? In the third number there. That's a 0. That is in the first row and the third column. Okay. First row, third column. And so I take 0, I multiply by -1 to the 1 plus 3 power. Okay, and the submatrix that results comes by crossing out the first row and the third column. And we get the submatrix 2, 4, 0, -2. And that's what we have here. The determinant of that. That's your third cofactor. And now you're able to get the determinant. Because all of these 2 by 2 determinants, we know how to compute a 2 by 2 determinant. Okay. And in the end, the result's going to be -2. All right, are there any questions on that? All right, well, and you can, so we expanded along the first row, but you could expand along any row or column and it'll work. Now, incidentally, sometimes what people do, like this -1 to the powers, you know, you have to have -1 to a certain power for each of your cofactors, right? And you notice, like for the A11, the number 1, it was a positive 1. For the entry in the first row, first column, we had a positive 1. For the entry in the first row, second column, we had a -1. For the entry in the, let's see here. Hold on now. There is, I think, hold on one moment. This should be a plus, by the way, class. It's not a big deal, but this minus here, it is a big deal. That should be a plus. Right here. That's a plus, not a minus. But you'll notice that we have a minus here. So sometimes, like, if you want to sort of avoid let me just see here, one moment. If you want to avoid the -1 to the power portion of the cofactor, there's an easy way for you to kind of see it. So that first entry in the top left corner, yeah, there is a no, Solomon. This here, that plus there should, that was a minus, that should be a plus. That should be a plus. But then you do have 0 times -1. Oh, I'm sorry. You know what I did? Hold on. I see. I'm sorry. No. Class, forget that. This is correct. Thank you, Solomon. Appreciate it. No, this is right. This was done by computing the 2 by 2 determinant. That's absolutely correct the way I wrote it. I guess I was thinking, I didn't read it carefully enough. We computed a determinant here, we computed a determinant here, but then we don't compute the last determinant because 0 times, 0 times whatever it is going to be 0. So this was correctly written. Thank you, Solomon. Appreciate it. All right, very good. Thank you. And you're welcome. And just to kind of help you make life a little easier. No, this is correctly, no. What I'm trying to say is I had misspoken. I had thought that this minus that I was talking about should be a plus. I was thinking, I was thinking I was computing the determinant. I thought I was working with the third cofactor here, but I was not. So we have a determinant here, we have a determinant here, and it's correct as written. So this minus is a minus because it's part of computing this determinant here for the second cofactor. So I just was misreading it. So okay. So there's a little diagram here. That you can use. This diagram here tells you like -1 to the first plus first power. Okay, -1 to the first plus first power. Right here. That's a positive. +1. -1 to the 1 plus third power. That's -1 to an odd power. That's a negative. Okay. -1 to the 1 plus 3. That 1 plus 3 is positive. It's even. -1 to the fourth is positive. So if you just, and this extended, this can be extended to larger matrices, but that'll save you from having to think about, having to put in the -1 to the I plus j power all the time. That'll save you from having to do that. How many kind of like that little picture there? How many find that helpful? I'm hoping you do. Okay, excellent, and excellent, Solomon. And so this is how you compute a determinant. Okay, this is how. So what it is you got like terms in front of your determinants when you do the cofactor expansion that can either be positive or negative. And so I'm putting in, the formula says put in the formula, -1 to the I plus jth power. You're doing it for all three of these things, right? Well, to save you from doing that, just keep in mind that in like where the 1 is, you're going to have a +1. Where the 5 is, you're going to have a -5 because there's a negative there. Where the 0 is, you're going to have a +0. That's all that is. It's just to save you from the worry of the -1 to the I plus jth power. So that's right. So like if you were say going to expand your determinant, say you were going to expand your determinant down the well, tell you what, let me do it right here. Let me do it right here in the board. Hold on here. Let me do it right here in the board. Yeah, we were going across the row. We were going across the row. So let's try let me see here. Let's try this determinant again. One moment. Okay, so hold on here. One, 5, 0, 2, 4, -1, 0, -2, and 0, right? Okay, so let's pick, we expanded along the first row. Why don't we expand along the second column? Okay, let's expand along the second column. Let's do cofactor expansion along the second column. So if we do that, we're going to have 5 times something times a 2 by 2, determinant of a 2 by 2. Then we're going to have plus 4 times something times another determinant of a 2 by 2. And then we're going to have plus -2 times something times another 2 by 2 determinant. Okay, so the 5, hold on here. One moment, class. Hello? Yes, this is he. Yes, I would like to give a donation. I would, but I'm teaching a class right now. Would you be able to call back maybe at 9:30? Okay, we'll talk then. Thank you. Okay, all right, bye. Okay, great. Sorry about that. So okay. What goes in here in the parentheses? A +1 or a -1? +1, good. Okay. And what's the submatrix going to be? Okay, it would be, so we're going to cross out the first row and the second column, so it should be 2, -1, 0, 0. All right. What about here? The next, well, are there any questions on that? All right, cofactor expansion. What about the 4? 4 times. What goes in the parentheses? A +1 or a -1? It's going to be a -1. That's right. So all I'm doing is I'm thinking about that little chart with the pluses and minuses. This number 4. Oh wait, hold on. No, wait. No, wait, we're wrong. Wait. No, we have this wrong. No. The 5, it's going to be 5 times -1. Because the 5 is in the first row, second column. It's just the chart for the plus or minuses. Yes, the exponents. That's right. That's what I'm thinking about, the chart for the exponents. So it's 5 times -1 times the determinant of the submatrix. And then the 4, well, the 4 is in the second row, second column. So 2 plus 2 is 4. 4 is even. -1 to the 4th is 1. Okay, but so this is going to be a +1. And again, you can just, again, think like this. Plus, minus, plus, minus, plus, minus, plus, minus, plus. This is how I'm getting the signs. This is how I'm getting the signs. Okay, so it saves you, right, that saves you from doing that work of those exponents. That's right, Matthew. And what's the submatrix now where for this, you know, for our second cofactor? Okay, very good. 1, 0, 0, 0. Yep, that's right. And then finally we have plus -2. Well, okay, we're gonna have a -1 there. Okay, because the, you know, there's the minus there. And what's the submatrix that's going to resolve? One. Yep, I'm getting 1, 0, 2, -1. Good, Wastina. Good. Are there any questions? All right. So let's compute our determinant then. So we're going to have 5 times -1. And then, of course, that's just going to be 2 times that determinant of that little 2 by 2 is in the first cofactor. This one here is 2 times 0 minus 0 times -1. And then we're going to get plus 4, okay, times 1. I mean, I could multiply that, right? But the determinant here is going to be what? 1 times the determinant here for the second cofactor is 1 times 0 minus 0 times 0. And then finally, we have, well, I'll keep everything in there. -2 times -1. And for this determinant here, we're going to have 1 times -1 minus 2 times 0. Okay, and what is this all going to equal then? Well, it'll equal -2. So you see you got the same determinant. First two terms are 0. That's right. That's right. Excellent, Christy. Wonderful, wonderful. You know, I'm wondering, we expanded along the first row, and here we did cofactor expansion along the first row, and now we did cofactor expansion along the second column. Is that the, you know, I mean, sometimes it's nice to choose I mean, since it doesn't matter what row or column we use to get the cofactor, since it doesn't matter what row or column we use to do our cofactor expansion, we're going to get a determinant of A equal to -2. What might be, might there be an easier, like, row or column to expand along? Might there be an easier one? Okay, Robin says row 3 or column 3. Okay. Well, Robin, why do you think why are you picking row 3 or column 3 to expand along? You're correct. Why? What makes row 3 or column 3? That's right, Mikhail. And I'm sure Robin and Christy agree, the zeros. The zeros. So when you do cofactor expansion, you traditionally want to expand along a row or column where you have the most zeros. Okay. Are there any questions on that? All right. If we're feeling good, well then let's. I want to look at an example in the book here as well. So let me bring up the book. Okay. All right. Let me bring up the book here. What I'm doing, if you want, you can go to your ebook. I'm looking in chapter 3, and I'm looking at section 3.1. Just got to find it here. Okay. All right, let me stop sharing here on this. We're all good here. And all right. Okay. Hold on here. I just want to get to, example 3. Okay, here they want you in example 3 to compute the determinant of a 5 by 5 matrix. And let's see, I can make this a little bigger. Okay, so we're looking here at example 3. That is a big matrix, isn't it? But what might be a good row or column to expand on? Okay, one moment, let me get to the thing here. Okay, so either the first column, that's right, Solomon, or the very last row. That's hold on here. That's correct, Christy. So the book, what they do is they decide to expand along the first column. And so when you do that, when you expand along the first column, you have, it's going to be a +3. And then remember what you do. You're going to let me just see, hold on here. You're going to, in your mind, remove the first row. I don't know if this thing will work. Hold on. Hey, how about that? How about that? Dr. Duty's getting there, right? So I'm crossing out the first row in the first column, and then this is the submatrix that results. It's 4 by 4. So far, are there any questions? All right, well, we're not done yet. Now we have a determinant of 4 by 4. So what, if we had to pick a column to expand along, what column would you choose? The first column, the first column. And so we will choose the first column. We will choose the first column. And so we would then, I didn't want to do that. Hold on. Getting a little better with this. All right, so we'll block out the first row, the first column. So it's going to be 3 times, okay, would it be 3 times a positive 2 or a negative 2? So we're gonna, it's like we got the 3. It's going to be a positive 2. That's right. Going to be a positive 2. Okay, and so now we have 3 times 2 times the resulting submatrix, the determinant of the submatrix. Okay. And does it, and then what would we, well, then this matrix here, we found it to be equal to determinant of negative 2. But this matrix was very nearly triangular. And it's saying to you that the method is adapted to prove, like we were basically, the 3 and the 2 were right on the diagonal. So what if this matrix were truly a triangular matrix where all the entries below the diagonal were 0? If that's the case, if A is a triangular matrix, then the determinant is just the product of the entries on the main diagonal of A. Did you notice that, how we were moving right along the diagonal? So we really like triangular matrices. They're our friends when it comes to computing determinants. Okay, they're our friends. Okay, now let me ask you, how long, so like, let's see. So how long do you think it would take to compute maybe well, this 5 by 5 determinant, it took about 5 minutes roughly, right? I mean, well, it would take a little longer. How many think it might take 10 minutes to compute that determinant? The determinant that we just did in example 3. How many thinks maybe it would take 10 minutes, maybe a little less? Using cofactor expansion. Good. And you want to use cofactor expansion in your homework, right? You want to practice that. You know, the next exam, I'm going to want to see cofactor expansions. Thank you, everybody. What if the matrix were 10? What if the matrix were 10 by 10? What if it were a 10 by 10 matrix? How long do you think it might take to compute a determinant? Christy's a little worried about that. Just make a guess. Make a guess. Long enough time to go, okay. 20 minutes, okay. It might take a little longer than that. 45 hours, okay. James thinks 45 hours, all right. Well, so Robin says 25 to 30 minutes. It's going to take a while for sure. How long do you think it would take to, if you had a computer and you were to, and the computer were to perform 1 trillion multiplications per second. I'm talking a computer that does 1 trillion multiplications per second. How long do you think it would take that computer? So that's a fast computer, right? I assume it's fast. How long would it take the computer to compute a 25 by 25 determinant? Let's say a 25-25 determinant, but you're not computing the determinant by hand. You're using a computer that can do 1 trillion multiplications per second. How long do you think it would take? Less than a second, a minute, seconds, less than 1 second? Okay. Well, actually, it's going to take 500,000 years to compute that determinant. Take a look. Look at the numerical node right here. If a computer performs 1 trillion multiplications per second, it would have to run for more than 500,000 years to compute a 25-25 determinant by the method we're using, the cofactor expansion. Fortunately, there are faster methods, but how many think that's yeah, so yeah, it's a surprising answer, isn't it? It's a surprising answer. Yeah, well, James agrees. It's a lot, and I'm seeing a lot of interesting emojis. And Matthew's right, assuming the computer can be that fast. So we really need, I mean, we love computing our determinants, but we need to find a faster way to compute our determinants. And this is where section 3.2 comes into play. And so, yeah, maybe, who knows, you know, well, this is something where, you know, I mean, PhD thesis, I don't know. So we'll move into section 3.2. We need a faster way to compute these determinants. So that's what section 3.2 is about. Let me stop the recording on this since we're going